Okay. So here, a few things I want to cover. We'll cover some of these things, discuss winding overload, EMI and EMC problems, inverter fault, cogging torque, torque ripple, control diagnosis, etc. So when you have a winding overload, some of the symptoms you can have is it doesn't start, slow speed increase, humming, smoke, smell. So winding can any kind of winding, even if one turn has a damage in the motor, you can have pretty bizarre behavior in the motor. So all of these are you may see. Sometimes you say, well, maybe my controller is not working properly. Maybe there's something wrong in my controller, but sometimes it is the winding that is causing the issue, that you have something wrong with the winding. And winding behavior is never consistent. When you have winding issue, the motor behavior is not really consistent, right? You can't say, well, it doesn't start because it's a winding issue. It may be that it is actually having a very slow speed increase, which is because the winding is damaged in the motor. Okay, you can have a humming, which also can be related to you have internal short in the winding, so as a result, there is a short circuit in the winding, which is causing the noise humming. So the cabling between drivers and motors and long cables, obviously these can cause an issue in terms of when you have a very powerful drive. Let's say you are dealing with a few hundred kilowatts of power, and you have to now the distance between the load and your inverter is 25, 50, 100 feet, whatever it is. So now you have got these switching voltages being transmitted through these long cables. And that long cable is going to cause EMI issues, which can also cause control issues because all of a sudden that noise is being coupled back to your controls. So it's very important to understand that anytime you have exposed cables and you have a switching voltages or currents being transmitted, you can have EMI issues around that area or around the controls. So obviously, when you're running it from the line, you can have the power line filter, the common mode choke. To the load, sometimes you can use essentially filtering here as well. But normally you do not use this kind of filtering for permanent magnet motors. Okay, you can have an LC filter here to ease the harmonics from the utility here. So there are some things you do in terms of easing your noise issues. Now, in case of you also have to think about that there's the bearing currents which flow through the ground when you have got switching. Okay, there's the coupling between your windings and your bearings, eventually your rotor and the bearings eventually. These coupling capacitors can cause current flow through your bearings, which can cause issues with your bearing as well. So that's something to keep in mind, that how the bearings can be electrically energized through your motor frame. Okay. And then in terms of inverter, well, I guess we're going to go into cogging torque solutions. So normally cogging torque is an issue where the motor does not spin smoothly. Although your controls are perfect, your motor doesn't spin smoothly because of the too much discontinuity between the rotor and the stator. So there are few techniques you can do in the controls. This is more of an issue, for example, in a BLDC motor where you have a trapezoidal drive. So if you have a trapezoidal drive, then you have more of an issue in terms of having cogging torque. So the solutions to that is introduction of dead zone in the rotor, introduction of tooth notching, using sinusoidal magnetization, and then also using the technique on your stator. So here are some examples here. So you have the rotor here, and then you have your two notch edges cancel SC1A. This is your interaction here with the rotor and stator, and you have two notches here. You basically are increasing your cogging frequency. You are artificially adding more stators without fundamentally altering your electromagnetic architecture. All right, so torque ripple, now normally torque ripple happens anytime your back EMF does not match with your back EMF or the current waveform doesn't perfectly match with your back EMF. Whenever, so the torque ripple essentially is the direct cause of a mismatch between your back EMF and the current injected into the motor winding. Okay, so of course there can be other causes which lead to distortion of back EMF. For example, your magnets not being magnetized properly, or your discontinuities in your stator or rotor can also lead to non-sinusoidal back EMFs. So in order to improve the back EMF, you can have skewing, fractional sock winding give you pretty good waveforms, short pitch winding, increased number of phases, air gap winding. So these are some of the ways to improve the back EMF so that you can have a sinusoidal excitation of your motor. In terms of improved control techniques, modified PWM control techniques, DC bus voltage control, current control based techniques, direct torque control, and phase. Now, this is mainly, I would say, related to BLDC, where you have trapezoidal control, where you can improve the trapezoidal control by using some of these techniques. Okay. So let's look at short circuit conditions at motor terminals, what happens and how can we detect them. And then we also look at internal, external power supply voltages and over temperature failure conditions that we need to have in the drive as a standard protection mechanism. Okay. So we're looking at a short circuit to ground, short circuit to battery, short circuit to line, weak short circuit in the microcontroller, Hall problem, and then MOSFET issues, right? Those are some of the issues we're going to discuss here. So in terms of, we can have on-state monitoring or off-state monitoring in terms of the issues we deal with in the motors. So let's look at this short circuit to ground. So when you have a short circuit to ground, so what you see here is you have a microcontroller section here, and then you have a hot bridge here. You have a battery on the top, and then you have a ground here, and you have a sensor resistor here. So with this, if you have a short circuit here to ground, essentially you have a shorted current being flowing, you're bypassing this resistor here, right? So you can, so one way is to monitor the drain to source voltage of this top MOSFET. And by monitoring the drain to source voltage, you know that the short circuit current is going to be V battery divided by the RDS on of this MOSFET. Okay. So if that short circuit current is greater than that value, you can set a threshold. You can set what is your arbitrary threshold between the drain to source voltage. You can say maybe it is 2 volts, maybe it is 3 volts. Whatever it is, because your battery is going to short to here. So I guess you're still controlling, let me see here, VDS threshold. So you can set your threshold across this drain to source voltage. And you can see here, you have a VDS monitoring here. And this VDS monitoring with the reference level, the threshold, you can trigger a fault. Okay, so you can basically say, okay, that is too much of a short circuit current. I need to shut down my inverter. Then this will require some kind of a calibration based on temperature. So here you can see what happens with short circuit current based on various temperatures. The short circuit current goes down and the resistance goes up. And you have a short circuit maximum value, minimum value, and typical value. So with this curve, you can set what your level should be in terms of triggering your microcontroller and shut it down. Then you have short circuit to battery. So short circuit to battery, essentially, you are connecting this point, middle point, to the battery here. So your short circuit current is flowing through your resistor and through your lower MOSFET. And the same thing you can do here is you can monitor this resistor here, and you can actually do a similar scheme where you have a threshold and you can trigger a fault once you exceed that threshold. And thereafter, you have a short circuit to load. So you have a load here, and now this is your two legs, right? So when you have a short circuit in the load, you're going to have this current flowing. So when you have winding short, or you have a short across the load, then you basically are going to have this kind of a current flow. And in this particular case, you are monitoring this voltage here and then monitoring this voltage here. So you're monitoring both of these devices, and then you are using a scheme to do basically you have two. Essentially, you're ANDing the two signals here to generate a single fault, which you can use for your microcontroller. So this is your HS1 VDS monitoring, and then this is basically says LS2 VDS monitoring. And both of these output, you have a threshold here for them, so that threshold can come from here as you are monitoring. This also is monitoring your short circuit to ground. So you can use the same threshold to trigger these two as well. Okay. And then we are going to the weak short circuit. The weak short circuit is the one which can be quite annoying and troublesome, where you can have multiple current paths. So here you have a PWM on phase, and you can see the current flow can go like this through the winding here. And your PWM off phase, normally your current flow is like this, right? And when you have a weak short circuit, you can see how the current is going to flow. Essentially, you have a weak short circuit, so you have a parallel path here. So in addition to this path, you are also going to have this path here because of weak short circuit. Okay? So you have two current paths to deal with when you have a weak short circuit current. And this weak short circuit, normally you are monitoring through your sense resistor if that is possible, and you have a threshold that you want to, if you exceed the threshold in terms of weak short circuit current, you can activate that part. So these are the circuits you can see for activating on-state and off-state faults. So don't have, so you have here the thresholds, short circuit to battery, on state, short circuit to ground. This is your short circuit to battery U phase and short circuit to battery W phase. So you basically have got V, U, and W phases here, and that is your activation for each of the phases: battery, ground, and battery ground. Okay. And let's see, here is your, you are monitoring your three-phase voltages, U, V, and W. And these voltages will change under short circuit to battery, short circuit to ground, and weak short circuit and winding fault. All of these four will change the balance of these voltages. So you can also use, essentially, one way to do it is if you have access to the neutral point, you can see where the neutral point is, and that actually can give you an idea of whether you have got a fault in the system. So you could use that as well, which is not shown here, but you normally are monitoring the U, V, and W voltages and trying to determine whether the system is in a balance or you have a fault indicator. So here is essentially if you have a supply voltage monitoring unit, you can monitor your battery voltage and logic supply. If you have a Hall sensor monitoring unit, you can determine Hall pattern error detection, Hall sequence error detection. Now, Hall sensor, you don't really need hardware. You can do that more in the software side of things. Logic clock monitoring, over temperature sensing. Over temperature sensing can go into the bridge, into your bridge overcurrent sensing. And the logic clock monitoring unit, where whether you have a fault on your if your microcontroller is not starting, that would require a hardware implementation where you can see if you have a fault because you have a issue with the logic clock. So you also require over voltage and under voltage. Now you can obviously monitor these with respect to firmware, but you can also have hardware implementation of these faults in case customer needs it. Some customers prefer to have some faults not be controlled by firmware. So you can have a choice as to give your customers a few options in terms of being able to shut down the inverter with hardware or with firmware. Here you're disabling your bridge through hardware when you detect these faults. So looking at the Hall code errors, let's say you have 3 Hall sensors and you have this north-south pattern. Your Hall sensors are within one quadrant here. So you can look at a gray coding where you can essentially make your Hall codes into a gray code, and thereafter you can look at the sequences and you can look at whether you are getting invalid sequences. So this is one hardware implementation of it, where you can implement with the combination of AND, NAND, and OR gates in a latch. You have a fault which can be used to disable your inverter. And here's another hardware implementation where you and I have a transition detection, 3 AND gates, OR gate, and latch to figure out fault detection mechanism. And this is an example. For example, this is your Hall sensor H1, Hall sensor H2, and then every transition you have this transition pulse, and then you have a transition pulse for H2 here. And then when you have a issue with your Hall sensor here, you're going to automatically generate a fault. And the fault will remain on for some time. Okay? And then you can clear the error, and then it can clear it. So that's one way to implement hardware side of things in terms of detecting all sensor faults. So this is your another way to figure out your logic main block issue. Then you can have an optional PLL here, pulse counter, and then you have a digital comparator here and digital comparator here, and then a gate here to get you clock fail signal. So that's one way to do the hardware implementation of keeping an eye on your clock. Okay, so over temperature sensing is essentially you need the over temperature sensing for power inverter block as well as for the controllers as well as the PCBs, and that can be directly routed to analog to digital converters and simple devices. So that was a quick overview of our faults. Any questions before we go to the next section? All right, so back into